Hey guys, in this video, I want to talk about ways to manipulate K. And so what that means is, if you remember when we were working with thermochem and we had Hess's law of summation, that's when we had different reactions with different delta H values and we had to make a goal equation. We don't have anything elaborate like that, but um, when I'm working with K, if I have a K value, and I want to figure out a K value for a different reaction. Maybe the reaction is reversed. Maybe the reaction is cut in half, or I put more than one reaction together to make a goal equation. I can manipulate the value of K rather than having to solve for new concentrations and plugging them into my K expressions. So this is manipulating K. It's very similar to Hess's law of summation that we did. So I just want to bring back some memories of Hess's law of summation and what we did. So if we multiplied a reaction by 2, what we did is we multiplied our delta H by 2 as well. That's how we manipulated delta H. Well, the reason why is because when I solve for delta H of the reaction, it's the sum, meaning I'm adding my products together. So sum of my products minus the sum of my reactants. So I'm adding those reactants together. And if I had more than one mole, I would multiply that value by, or multiply that number of moles that I've multiplied by the delta H. And so if I doubled an equation, then I doubled delta H. Now, if I do that for K, it is a little bit different because you see how these coefficients are multiplied through my products. Well, here, our coefficients are raised to the power. So if I multiply a coefficient for K to find a new K value, I have to raise it to that power. So for instance, if I multiply 2 throughout a reaction, to alter K, I got to raise K to that power. If I take a reaction and I cut it in half, then to manipulate K, I raise it to the 1/2. And raising K into the 1/2 is the same thing as taking the square root. Now, let's talk about reversing an equation. If I flipped an equation when I was working with delta H, then all I would do is flip the sign. The reason why is because it's products minus reactants here. But let's look at K. K is products over reactants. So if I flip an equation, you see how I'm flipping my products and my reactants here. So reversing an equation, I have to reverse K by taking the reciprocal. So 1 over K. Now let's talk about adding multiple equations together. Well, for delta H, if I add multiple equations together, I was just adding more and more products. Well, I would add my delta H values, and that's because my products are just adding upon each other. But if I have more than one product for K, I multiply those products together. So if I'm adding equations, I have to multiply my K values together in order to get my new K. Now, this might be a little crazy, you might not really understand, but let me do some example problems to make it all make sense. So I'm going to clear my little palette here. So looking at exercise 3, we want to calculate a K value for an equation called the Haber process. Now, this is something that is like common knowledge to all chemists. So anytime you hear the Haber process, you should be thinking, oh, production of ammonia. This is something you should know by heart. When I produce ammonia, it comes from N2 nitrogen gas plus H2 hydrogen gas. And we're working with double arrows now because we're in equilibrium. That's producing ammonia, which is NH3. To balance this equation, I need a 2 here and a 3 there. So this is known as the Haber process. It's the production or formation of ammonia. So first of all, we want to calculate our K. Now, this temperature is not really involved in our K. All that we have to worry about that is if our temperature changes, we know our K changes. So it's not changing, so we don't really care about it. So to figure out my K value, I first want to write my equilibrium expression. So we're going to write it using this equation here. So I have molarities here. So the type of K that I'm going to write is a Kc expression. So I'm going to use brackets, NH3 raised to its coefficient, which is 2, over N2 raised to its coefficient, which is just 1, times H2 raised to its coefficient, which is 3. Now, always double check, is there any solids here? Is there any liquids here? Because I can't include them. Well, all of these things here are gases, so they're safe to put into our equilibrium expression. Well, now that we have our equilibrium expression, what I'm going to do is I'm going to plug in each of these values. So 3.1 times 10 to the negative 2 goes here. 8.5 times 10 to the negative 1 goes here. And 3.1 times 10 to the negative third goes there. So I would take this squared divided by this times this cubed. And when I do so, I get a K value that's equal to 3.8 times 10 to the fourth. K also does not have any units. I like to say it's like a little jaybird. It's just running around being all naked and stuff. It doesn't have any units attached. Units are kind of like clothes. Get it? Okay, funny. I know. So anyway, we have our K value here. Now, this part B and part C is where we're manipulating this equation. We're changing it somehow. And because we're changing it, we can manipulate this K value. So let's look at this equation and figure out how it's different from our beginning equation. From what I see, this equation is just the previous equation flipped, right? It's reversed. So we ask ourselves, well, if I reverse my reaction, so that says K for the reverse reaction, what does that mean? Well, what I've done is I've switched these products and reactants. And because I've switched these products and reactants, I have to take the reciprocal of this value here. So 1 over K. And that's the rule that we see up at the top of the notes. If I reverse a reaction, I take 1 over K to find the new K value. So 1 divided by 3.8 times 10 to the fourth. I plug that into my calculator, and the value that I get is 2.6 times 10 to the negative fifth. No units, naked little jaybird. That's my answer there. It's a lot easier than setting up a new K expression and plugging in those molarities to solve for K. Now, you definitely can do that. That's totally fine. You'll get the same answer. But one, it's faster to do it this way. And two, sometimes they'll just give you this value and expect to find the new value. You might not get those values there. Okay, let's look at this last example problem. So what we have for part C is we want to figure out the equilibrium constant, same temperature, so we don't really care about it, for the equation. Now, the equation that we had at the beginning and this equation, how it's different is it's all divided by 2. So basically, you've taken half of your original K. Now remember, the rule is, if I take an equation and I multiply it by some number, I gotta do K raised to that number. So half of my reaction, the new K, is equal to K raised to the 1/2. Anytime I raise something to the 1/2 power, I'm essentially taking the square root. So 3.8 times 10 to the fourth, I take the square root of that value, and that's equal to my new K, and that value ends up being 1.9 times 10 to the second. And that's all you have to do. I've seen this in multiple choice, and I've also seen this on free response. So the only time when you really have to apply this is if you have a K value and you have a reaction that is altered a little bit. Maybe it's reversed, cut in half. Maybe there's two equations put together to make a new equation. And all I have to do is manipulate K to solve for those new K values. So I hope this is helpful. Hope this will get you some multiple choice and free response points.